In this problem, we've got water flowing over a flat plate, and it flows in the x direction only. We know the speed of the water far away from the plate is equal to 0.3 meters per second. So by far away from the plate, I mean at large values of z. We also know that the plate is infinitely wide in the y direction. We're going to assume that the value of y does not impact the fluid flow. Based on experimental measurements, we know at Reynolds numbers smaller than 500,000, the flow is laminar, and for Reynolds numbers larger than 500,000, the flow is turbulent in nature. So we want to figure out a few things. The first thing, we want to describe in words where the flow is laminar. So in other words, where in this diagram is the Reynolds number smaller than 500,000? Well, to do that, let's write down the definition of the Reynolds number. So we'll use the subscript x representing the length scale that we're looking at. And the Reynolds number as defined here is equal to rho times u infinity multiplied by x divided by the dynamic viscosity. So what we're going to find is that at small values of x, the Reynolds number is smaller. So in fact, at x equals 0, right here at the leading edge of the surface, the Reynolds number is equal to 0. And as we move downstream to larger and larger values of x, the Reynolds number at these locations is growing larger and larger. There exists a certain value of x in which the Reynolds number for that value of x is equal to 500,000. And at that value, what this says is that at all values of x larger than that particular value of x, the flow is going to be turbulent, and for any regions with values of x smaller than that, the flow will be laminar. For part 3 in this problem, we want to figure out the value of x at which the flow transitions from laminar to turbulent. And we know again that the Reynolds number, if it's larger than 500,000, it'll be turbulent. If it's smaller than 500,000, it will be laminar. So let's rearrange this expression. We'll solve for x. And after solving for x, we can plug in values. We know that the dynamic viscosity for water is equal to 0.001 Pascal seconds, the density of 1,000 kilograms per cubic meter, times u infinity, which in this case the water is flowing at 0.3 meters per second. We multiply that by the critical Reynolds number of 500,000. We find that this value of x is equal to 1.7 meters. So for all values of x smaller than 1.7 meters, we'll find that the flow is laminar. And for values of x that are larger than 1.7 meters, we'll find that the flow is turbulent. And for part 4 of this problem, we're going to switch the water out with air. So now we've got air flowing over the surface at the same speed. And the question is, does that transition from laminar to turbulent, does it occur closer to the leading edge, or does it occur further away from the leading edge when we switch out water with air? So to do this, we'll just plug in the new material properties for air. So instead of 0.001 Pascal seconds, the dynamic viscosity for air is 1.8 times 10 to the minus 5th Pascal seconds. And similarly for the density, instead of 1,000 kilograms per cubic meter, the density for air is 1.2 kilograms per cubic meter. So we calculate a new value of x. Again, we're looking for a location in which the Reynolds number is equal to 500,000. We find that this new value of x is equal to 25 meters, which is a great deal bigger. Recall for water we had a value of x that was equal to 1.7, and now we're at 25 meters. So in this case, when we switch out water with air, we'll find that the transition from laminar to turbulent flow occurs further from the leading edge, much further in fact, 25 meters versus 1.7 meters. The reason this is the fact that the density between air and water changes by 3 orders of magnitude. We're going from about 1 kilogram per cubic meter up to 1,000. However, the dynamic viscosity changes by only 2 orders of magnitude. So the viscosity for air is less, but only by about a factor of 100. So the relative values of those 2 parameters result in a transition from laminar to turbulent that occurs much further from the leading edge of the plate.